Let's do some of these related rates problems from your practice test. So problem 7, it's about the same tank that we used for problem 6. I have a rectangular tank. I've been told the volume is length times width times height, normal for a rectangular tank. I've been told that the length and the width are 10 and 20. What else do I know? I've been asked to find the rate of change of the volume in the water in the tank at time t equals 2, and to give units with my answer. So I'm not working on question 6. This is just a convenient place to work in here. So find the rate of change of the volume of the water. So that sounds like the thing I'm looking for is, I don't know why I always just use this word. I seek dv dt, specifically dv dt at time t equals 2. So what are some things do I know any rates of change already? It wasn't very specific here, but I think you need to practice understanding what's going on even when I'm not specific. I do know something about the rate at which the height of the water is changing. So I know volume is length times width times height, and I know something about how fast the height of the water is changing. That would be called dh dt or h prime of t. So I seek dv dt at time t equals 2. I know dh dt, which is the same, I know dh dt at time t equals 2. That's the same as h prime of 2. So that's just our job to know that those two notations, dh dt evaluated at a certain time value and h prime of 2, mean the same thing. So can I find the rate of change of the volume? I claim that I can. So I'm going to write this equation. I know volume is length times width times height, but think about when a rectangular tank fills with water. Like the first drops of water are going to spread all the way out, and as soon as possible, the water is going to take on a rectangle shape. And after that, as long as water keeps going in, the length and the width of the rectangle shaped water is going to stay the same. It's going to be the same as the length and width of the tank, and the only thing that's going to change is the height. That means in this case I can think of length and width as constants, and I'm going to write this equation. I'm going to write V, the volume, is equal to, I could write length times width times height, but I know length is 20, width is 10, so I'm going to write 20 times 10, 200 times h. So that's this equation that was handed to me, except I've been able to replace the length and the width with their constant values. Those values do not change, so I'm not breaking anything by plugging in the values right now. It's not that I'm plugging in at a certain frozen point in time. It's just length and width are always 20 and 10 in this problem. So now I need dv dt was the thing that I wanted, and that's not so bad because I can take the derivative of both sides of this equation with respect to time. I'm just going to skip over this. I'm just continuing my work here. So the derivative of v with respect to t is called dv dt. The derivative of 200h with respect to h is 200, but the derivative of 200h with respect to t is 200 times dh dt. I'm going to jump back up here, just move that out of the way so I have more room. The thing I was looking for was dv dt at the specific moment when time equaled 2. So I'm simply rewriting this equation, but I'm freezing it at the moment when time equals 2. So dv dt equals 200 times dh dt is the same as saying dv dt at time t equals 2 is 200 times dh dt when time equals 2. Well, dh dt when time t equals 2 is the same as h prime of 2. And I know that. So that's going to equal 200 times 0.5. which is 100. I've been asked to give units with my answer. And there's two ways to get this answer. I can think about this value I've reported. I know it's the rate of change of volume with respect to time, and I can give units of volume divided by units of time. So volume units are the inches. Inches cubed, in this case for volume, divided by time units, in this case, are, what are they? Minutes. I have another option, which is I could go back to this equation. 200 came from multiplying 10 inches by 2 inches, and I know the units on dH/dt. Well, maybe I don't know units on dH/dt, but the units on h are going to be inches. So the units on dH/dt are going to be inches per unit time, so inches per minute. So I can think about those units. They came from multiplying inches times inches per minute, which makes, again, inches cubed per minute. Your final answer, 100 cubic inches per minute. Another related rates problem from your practice test is number 8. Sand falls from a conveyor belt at a rate of 10 cubic meters per minute onto top of a conical sand pile. Conical meaning shaped like a cone. And I've been told that the volume of a cone is 1/3 pi. Oops, I see that you can't see the pi. But that's 1/3 pi r squared h. I'm pretty sure it printed fine on your paper. And I have this one other fact that's very helpful here, is I've been told that for some reason, because of the way this sand works, or for some reason, the height of the sand pile is always 1/2 of the radius of the cone-shaped sand pile. So going into this problem, I have this fact I want to keep in my back pocket. The height is equal to 1/2 of the radius. So I'm not saying that they would typically do this for you on the AP test, but here I sort of split this up into two parts. It's just a reminder that if I'm going to do a related rates problem, which it turns out letter B is, I'm going to need a formula that contains, well, I don't actually need a formula that contains one variable, but it's way easier if I have a formula that contains one variable, because then I won't have to use the product rule. You might remember that third example down on our 4.6 notes, when I had the volume of a cone and I had to take the derivative with both. I'd use the product rule because I had both radius and height. I had to split it up and made taking the derivative longer. So for part A, another way to get around that, we didn't do an example of it in your notes, is you could try to just write a one variable equation. So we're going to write volume as if it were a function of radius alone. And I'm going to be able to do that because everywhere I see h in my volume formula, I'm going to replace it with 1/2 r. So I'm going to start with this equation. Volume is 1/3 pi r squared h, but I'm going to replace h with 1/2 r. Volume is 1/3 pi r squared, but instead of h, I'll write 1/2 r. Now that's fine. You have no obligation to simplify that expression, but in part B, I'm going to have to take the derivative, and it's going to be much easier to take the derivative of the volume if I've simplified this expression. So I'm just going to, because I have more room right here, I'm going to rewrite volume as the 1/3 multiplies by 1/2 to make 1/6 pi r squared times r makes r cubed. Okay, so now I can get along to letter B. Letter B asks, how fast is the radius of the sand pile changing at the moment when the height of the sand pile is 4 meters? So that makes me want to write myself a note. The thing I'm looking for, how fast the radius is changing, that's called dr dt. And if I'm going to be really specific, I want dr dt when h equals 4. But that's a little unfair because h is not a r. But that's okay, that's what I'm looking for. And here's another question. We said we want to answer a related rates problem. We want to think about any rates we're looking for, dr dt, and any rates we might already know, because we want to make sure that the equation we write contains both of those variables, not their derivatives, but both of those variables. And it turns out we have to understand that this is actually an important piece of information. Sand falls from a conveyor belt at 10 cubic meters per minute. So that means every minute, 10 cubic meters of stuff is getting added to this cone-shaped pile. That's increasing the volume of the cone-shaped pile by 10 cubic meters every minute. So that is, I'll write up here that we were seeking dr dt. We know, that's KNOW, we know dv dt equals 10 cubic meters per minute. All right, so and now I know I need to write an equation that relates v and r, and I've already been set up because I have that. I wrote that as part of my answer to letter A. So I'm going to start with v equals 1/6 pi r cubed. I'm going to take the derivative of both sides so that I have an equation that contains both dr dt and dv dt. So dv dt, the derivative of 1/6 pi r cubed with respect to r is 3 times 1/6 times pi r squared. But I wanted to take the derivative with respect to time, so I'm going to have to multiply by dr dt. Okay, that's not so bad. I'm looking for dv dt, and I already have a formula for it. I'm going to be able to multiply 3 times 1/6 times pi. dr dt, oh, I'm sorry, I don't know dv dt. That's the thing. No, I do know dv dt. I'm going to be able to replace that with 10. I'm going to be able to multiply 3 times 1/6 times pi. And I want to isolate dr dt. That's the thing I've been asked to find. Here's the problem. I have one more variable in my equation. I'm going to have to be able to replace it. Otherwise, I'll have a two-variable equation. I won't be able to solve specifically. So I'm going to go back to, I've been asked when the height of the pile is 4 meters. I'm going to go back to that equation I started with. So 4 equals 1/2 r. Multiply both sides by 2 and decide that at the moment when the sand pile is 4 meters high, it has a radius of 8. So I'm going to